Welcome back to Root Access. Today we're talking to Vinitra Swamy about her work InterpretCC, Intrinsic User-Centric Interpretability Through Global Mixture of Experts. Hi Vinitra, thank you so much for joining us. We're excited to talk about your paper.
Hello, super nice to see you, Allison. Thank you so much for inviting me. It's so great to be here.
Yeah, so I'm really excited to dive into interpretability. Obviously, this is a exciting topic right now, especially as, neural networks become more prevalent in all aspects of our lives. Before we get into that, though, I just want to kind of get an understanding of your journey into machine learning in general, and then also this space in particular.
Yeah, sure. That makes a lot of sense. I guess I've been in kind of the machine learning space for a while. Back when I did my bachelor's and even my master's, it was just about the time of this kind of large ramp up. Like this is what, 2015, 2016. And when I was at Berkeley, we were just starting to offer data science courses. So our intro data science course, the first semester I was there was 100 students. By the time I left, I was head of the course staff for it, and it became 1,700 students a
Oh, wow.
semester, and then this giant MOOC. It was really, that hockey stick. So basically, in my first year, I joined a few research labs, and then I ended up deciding on the Berkeley Institute for Data Science. I wasn't so familiar with data science at that time, but I just loved the people and I loved the idea. And it really was, I think, the most exciting place to be on campus around then because just everything was growing so fast and everyone was so excited and all corners of campus were involved. I think
Right.
the appeal for me with computer science is that it's kind of a tool that you can use to understand a lot of different fields. And data science perfectly embodies that. We would be implementing like cool ways to understand Eastern Assyrian texts and at the same front, like analyzing a lot of cancer data or financial data or things like this. So it was a really nice way to bring everyone's interests from across campus into kind of how computer science can be involved for them. And I think the teaching community there, especially those who are involved in TAing and stuff like this, were just the most amazing people to be around because they had such diverse interests and diverse ways of viewing data science. It was really a special place. And so, kind of from there, it was inevitable I would become a machine learning scientist.
And what draws your interest, or what's the motivation, I guess, for this work in particular?
Yeah, this work has had a very interesting journey, especially over my PhD. So, at the beginning, when I started my PhD, I was really, really interested in explainable AI. I had just worked for a few years at Microsoft AI, and I saw that a lot of the customers there were kind of using older models because they were interpretable instead of using kind of newer neural networks and things like that were coming out around that time. And it was just shocking to me that they would prefer these models, but the reason that they preferred them was because of interpretability. So I thought
Right.
with my PhD, I wanted to find a way to answer the question of how can we maintain these advanced models, keep all of the advantages of these, but also design architectures in a smart way to not lose that interpretability. And that's kind of what this paper seeks to solve. So in my
Right.
PhD, I was evaluating a lot of these initial explainability methods. Probably some you might have heard of before, LIME, SHAP,
Yeah.
counterfactuals. They're kind of like really big names in the field. What happens there is that you usually train a neural network and then you have an explainer that sits on top and tries to predict what was important in making this decision from the neural network. But what we found early in my PhD was that a lot of these explainability methods disagree with each other. For example, students for the same models of like in the education domain. And this was really a concerning result because what that means is which explainability method you choose determines what kind of explanation you get, which
Right.
is a super big problem. So then I kind of turned my attention a bit to this interpretable by design neural networks. How can we design models that give you guaranteed interpretability? Like this is for sure the explanation that you want out of the model. And that's what we seek to do with this work, kind of getting that interpretability guarantee with using a state-of-the-art architecture and trying to do to give those explanations in a way that is user-friendly, that
Yeah.
actually is a way that we can act upon the explanation.
Okay. I want to jump back a little bit to the problem space, just so that we're laying the foundation, we're all on the same page. Why is interpretability so important, particularly as we get into sensitive areas where we're going to start to see this technology deployed?
Yeah, great question. So why is interpretability important? I'd say that it's for a few main reasons, right? One, especially in these human-centric fields, education, healthcare, anything where a human and AI work together, it's really important and crucial to build trust in model decisions, or otherwise the adoption of these methods, face a lot of disadvantages. But then the second reason I think is with auditing model mistakes. So, okay, well, on one side, you're building trust in the methods, but on the other side, even if these methods are 99.999% trustworthy, when they make a mistake, you would want to see why. So even if it has a correct prediction but a wrong reason, I think that's when the human should, intervene and say, okay, but this prediction is still correct. Or even if they have an incorrect prediction for incorrect reasons, that's exactly when a human needs to be involved. Because in any of these situations with real world impact, we cannot blindly trust AI decisions. I mean, we've all used ChatGPT. We've seen different cases where it's been doing extremely well and extremely confidently wrongly.
Right,
So
right.
explainability aims to address this problem.
Okay. Now, talk to us a little bit about conditional computation. What is it and how are you applying it to your work?
Great question. So conditional computation is this concept introduced by Bengio et al. Of course, he's made so many papers. So one of those amazing papers from way back when. But it's all about taking different pathways through a neural network model such that you can, the way that they framed it originally was for efficiency. So you don't need to use the whole model every time to make every prediction. That's kind of the premise behind conditional computation, because you're conditioning on which parts of the computation you want to. We think that this kind of approach can be used also for interpretability objectives, as opposed to just making models run fast. So instead of having conditional computation with no specific areas that you're deciding and giving names to and realizing what they mean and what they specialize on, if you do it in a general way, you can get really fast with fairly simple architectures. And it's a great idea, but we're basically extending this for an interpretability objective.
Okay. And you talk about four requirements for human-centric explanations, and you kind of alluded to the importance of having the results be something that are, you know, palatable to read and to understand. So talk to us about what those four requirements are, and what do they mean?
Yeah, for sure. There's a lot of these different requirements outlined in a lot of different explainability literature about what makes a good explanation. And this was our attempt to synthesize and summarize these, especially for the context of these interpretable by design neural network models. And by that, I mean architectures that are inherently explainable in some way, but are still a deep learning architecture.
Right.
So maybe outlining the four requirements. The first one that I was discussing is granularity. So some of these methods work on the basis of a single feature, which maybe you have like say 45 features or hundreds of features or something like this, which we know about before, or concepts, which are either groupings of features or some other kind of concept that you specify in some way, or that is extracted from the model and then you're trying to give a name to afterwards. There are also a few examples, not so much mentioned here, that are based on examples. So the concepts are basically examples existing from the underlying data set. So that's what we mean by granularity. What kind of explanation do you want? And then we have this notion of faithfulness. So faithfulness is all about, does the explanation align with the model's internal decision-making process? Is what the explanation is saying actually what the model is doing? Then there's sparsity. And sparsity is all about this understandability stuff, right? Because if you have an explanation that's talking about 20 features or 50 features, etc., yes, it might be right. Yes, it might be what the model is doing. But is it actionable? Is it understandable? Can you make a decision based on it? It's really hard, right? So sparsity is all about, can we make the explanation as sparse as possible such that a human can act upon it, that we know that it's these three things that made a student, let's say, predict to fail in a course or something like this. And then there's the notion of coverage, which also goes by a few other names as well. But with coverage, what we're trying to say is that, does the explanation cover the entirety of what the model is doing or only partially? Because an explanation can still be right, and be partially correct, right? Like it only reveals some part of the model decision-making process, but it is truly what the model is really doing. But coverage means, does it for sure cover all aspects of what the model is doing? There's no
Okay.
variability in what it is.
Okay. Now you mentioned two intrinsic models that are the most relevant to your approach. I'm going to read self-explaining neural networks and neural additive models. Talk to us a little bit about those. What are the similarities between the three?
Yeah, for sure. These are great papers, by the way. I really, really look up to them and respect them. NAM is the neural additive models. It's similar also to the concept of explainable boosted machines, if you've seen that before. But what NAM basically does is that it takes each feature, and for each feature, it gives its own network. And then the prediction is kind of a sum of all of these scores that are generated from all of these networks. So each feature contributes a certain amount to the prediction, and you know exactly what that is. And the prediction is actually a linear sum of all of these results from all of the features. This is super nice, but you can probably imagine that it doesn't really take into account inter-feature dependencies, right? That two features actually make sense to be treated together. SENN is, on the other hand, a bit more on the concept side. And it's also based on the prototypical examples that we were saying before. What SENN does is that for its use case, it creates a certain set of concepts. So from the feature space, it selects these, let's say, 5 concepts or so many other concepts it describes. And using these 5 concepts, it creates a score for each of those concepts. And the prediction is a sum of those concept scores. And the concepts are described by examples from the data set. Now you can imagine in kind of the image or the vision domain, it's kind of really easy to look at the images of things and see, okay, yeah, that's the concept that it's providing because it's stripes for a zebra or something like this, or beaks on a bird. But in kind of the domain that we're looking at, which is a lot of time series data with kind of human interactions, human behavioral data, click streams, it's really hard to interpret these as examples. And that's why, even though these example methods work really well for these kind of domains, and maybe even for audio domains, or sometimes even for video domains or things like this, it doesn't really work well for this time series domain, and maybe not even the text domain either.
Right. And that kind of leads into my next question. So you have two architectures, feature gating and the group routing. And I think you're alluding to a little bit of the grouping there because the different data sets, if my understanding is correct, the different data set types, you have a different grouping method. Um, Correct me if I'm wrong there, but talk to us a little bit about the importance of the two architectures, and then we'll get into the grouping and how you went about doing that.
Sounds great. So let's talk first about feature gating versus group routing. Feature gating is basically the easiest way, right? The one that involves the least human effort, the most similar to a normal architecture. What happens is that you have a set of features, and maybe these features are distributed over a time series or tabular data, or that you have text data or something like this. But like for simplicity, let's say we're taking a tabular data set with a set of features. What feature gating does is that we have a set of discriminator layers that basically picks for each entry that comes in. And let's again take the case of a student. We're trying to predict early in the course that they're going to pass or they're going to fail, such that we can give them some additional help before they reach the end of the course, such that they really don't fail the course. Okay, so given this use case, we have all of these features. For each student, we activate certain features. So out of the 45, let's say for an easy to classify student, we only activate 2 features or 3 features. And the prediction is only made using those 2 or 3 features for the student. Now, maybe a certain harder to classify student has some sort of complex behaviors or something like this that doesn't fit into regular patterns, might take 6 or 7 features as opposed to the original 2 or 3. So the explanation there becomes a bit more complex, but we're not trading that for accuracy. It's as sparse as it could be to maintain the performance.
I'm gonna interrupt for a second.
Yes.
Let's say in that use case, how are the features selected on which ones are going to be weighted more or evaluated first, and which
Right.
ones will be added after?
Yeah, great question. So the features are just yes or no, right? There's no
Okay.
adding them later. So the key is we're looking at all of the features together to select which features are important to make the decision on. Because oftentimes
Okay.
there's a lot of noise in kind of selecting features you don't really need to make the decision. So basically we're making it really concrete. And this won't work in every single use case, but we're showing that it works in actually a lot of these human-centric use cases. And the way
Mhm.
that we select which features are important is through this discriminator layer that's forcing us to pick only a few features. And the way it does that is through a really nice trick called the gumbo sigmoid trick. It's basically picking those features from a probability distribution, the ones that are most important. And only those features are passed to the prediction module to make the prediction. So we are sure that our prediction for this person was only made using these features. But we selected the features adaptively, right? Like for each student, we can select different features based on their overall performance to make the decision.
Okay. All right. That makes sense. Now, group routing.
Yes, group routing. So group routing is closer to a traditional global mixture of experts model. So that's why it's in the title of the paper. Mixture of experts models from just a high level are basically a larger model with a lot of submodels, and the submodels all specialize in different parts. So it's like a group of these different experts, and different ones of them are activated at different times. Now, traditional mixture of experts architectures, and ChatGPT is suspected to be one, mixed role, etc. There are a lot of them appearing in our daily lives. They work on a layer by layer basis. So each layer, it picks, let's say, 2 experts to use, and the experts specialize on different areas. Maybe not interpretably. We don't know which areas each expert specializes on, but they all specialize, and at each layer, you're picking 2 experts to set. Instead of doing this at each layer, we're doing this once over the whole model. So what's happening here is that we have all of our input data. It feeds into the discriminator network, and this input has been now grouped into concepts. And we can talk about later how these concepts are defined, etc. But let's say we have a grouping over our feature space into concepts. And unlike SENN, which kind of does it by showcasing the prototypical examples to represent a concept, where certain features can be in multiple concepts, this is a linear separation. So each feature can only be in one concept, unless you want to relax some of the interpretability guarantees. All right, so now we have these concepts for the input space. And with our discriminator network, we're trying to show which ones of these concepts should be activated. And only those concepts are activated. So let's say take the student watching, student interacting with an online course setting. Only the student's video watching behavior and the regularity behavior, how often they log on, are used to make the prediction. And nothing else. None of their assignments, none of their quiz scores, nothing else was involved. And in that way, you know exactly that, okay, this student maybe was predicted to fail because of their video watching and their regularity behavior. Right. So I can design an intervention exactly to say, hey, maybe you want to watch these videos in this week that's upcoming, or hey, maybe you want to log on more regularly. Like you can give these personalized interventions through this kind of user-centric interpretability, decision-centric, or even, I guess the way that we phrase it in the paper and also our mindset is that we want it to be actionability-centric interpretability, where the interpretation only matters so much as you take an action based on it afterwards.
Now, is it correct that you use different grouping methods depending on the data set type?
For sure. So great question. We did use totally different grouping methods based on each data set. So it wasn't even by data modality, it was by data set. Because if
Okay.
you look at the breast cancer data that we were using, it requires a very different grouping methodology than, for example, the text data that we are doing news classification on. So I can talk about how the grouping works for each of them. For the education case that we were talking about, there's a couple of different grouping methods we tried. We actually tried 3 in the paper. So the first is rooting by paper. So each of the features that we had, which were 45 features times 10 feature weeks for each course, and we tried multiple courses as well, are coming from different research papers. So we said that someone who introduces a feature from the same research paper is talking about a very concrete topic. So we grouped them by the original authors of those features. That was kind of try number 1. Try number 2 was grouping them in human interpretable concepts. So in the literature, there's been exactly what I was talking about before: regularity, proactivity, these kind of concepts that the features can be grouped into: high effort, consistency, those kind of things. So we used those, which we call rooting by pattern. That comes from a very cool paper in the space. And then the third way we called rooting by language model, because given the descriptions of all the features, we found that GPT-4o is actually really good at grouping features into human understandable concepts. And so we can just use those concepts in the model. Now, for the text data sets, we did something quite interesting. Are you familiar with the Dewey Decimal Code?
Yes.
Yeah, with the library system. So
Yeah.
the way that Dewey Decimal Code works is basically in any library, you know, for a specific topic that it's classified in a specific shelf, right? Because of all the listings of the numbers and how the numbers relate to each other. So it's this like huge classification of all the topics that anyone could write books on into sub and subcategories such that you have ID numbers for each topic. So we actually use the Dewey Decimal classification and group them into the 10 higher Dewey Decimal categories. And the way we did this was because of let's say that we're trying to classify a news article into a certain domain. To identify which topics might be relevant for helping classify this news article, we looked at the text embeddings of the content of each entry, which was only like a few sentences, and we compared it against the concepts, which were represented by all these Dewey Decimal headings and subheadings.
Okay.
And the hope was that we are activating the groups that are most relevant to what was actually the entry of the news article. So we had a specialized network for each of these higher level categories. And there were many categories. I think there was one, a larger one on sports, a larger one on like kind of science, a larger one on a lot of these different areas. And so you can have experts that specialize in topics that are relevant to each other instead of specializing on everything.
Okay.
And then lastly, with the breast cancer case, there are lots of different ways to do it, and we're definitely not medical experts. So we hope that the doctors that use our model would find an even better way to do this kind of classification. But we had different cells and different features, and each cell was viewed differently and taken from a different area in the breast cancer tissue. So it was basically trying to identify whether this person has breast cancer or not. And so we grouped by cell. But it would be totally reasonable also to group by some larger feature group based on your knowledge of the medical domain, that these features actually mean a lot together. And because
Yeah.
I have these features, I want to make this decision based on it. For us, the decision was we want to know which cell is carcinogenic if we have 3 cells in a sample together. So because of this cell, we decided it was carcinogenic because of these features in this cell, let's say. So we wanted to look in that way.
Okay, and now share with us your results, how your InterpretCC performed, and I'm interested also in the performance based on the type of data uh,
For
that
sure.
was evaluated.
Uh, So with our evaluation, we tried to prove a couple of different things. The first experiment we did was trying to show that this kind of model doesn't compromise on performance compared to even normal baselines without any interpretability,
Hmm.
as well as these other interpretable by design baselines. And we saw that in a lot of cases, the confidence intervals overlapped. And in some cases, we were significantly higher than the non-interpretable module, the way that a model is trained right now. So actually, interpretability can have some performance advantages. In a few cases, we were not as good with the feature gating as with the group routing in comparison to other models, and that was mostly with the health breast cancer data set. We did much better with the group routing, which means like when we grouped by cell, we had a much better performance.
Right.
But with the feature gating, we did a little bit worse. Not a lot worse, but a bit worse. So it is interesting, the question that you asked about which kinds of data formats do we do better on or worse on. We did quite well with the synthetic tabular data set, so I wouldn't say we did so bad with tabular data in general. We did significantly better than the other baselines. But I would say that for the health case, there is something interesting there about why feature gating didn't work as well.
Yeah. Yeah, so it's not across domains necessarily that the feature gating works better or worse. It could be an interplay between the type of data, the domain, what
The
you're trying to
grouping,
look at,
yeah,
the
exactly,
grouping. Yeah.
exactly. Um,
Okay.
so that was the first thing that we tried to prove. The second thing we tried to prove was the faithfulness of the explanations. And for
Hmm.
this, we compared our results on this data created by the OpenXAI group. That was a nice paper and leaderboard from a Harvard group a few years ago. And it's a synthetic data set, which basically means that it constructs this kind of deep learning task. But in fact, there is some kind of ground truth of the data where that the combination of the feature y is of these 3x's in some way, or at
Right.
least exactly. So we evaluated on this set, and we found that feature gaining and group routing do fairly well in comparison to whatever the ground truth underlying expectation of the model is. in fact, better than SENN and NAM in a lot of cases, and sometimes also better than LIME and SHAP, which just sit on top of an existing model. What is really interesting, though, is the cases where InterpretCC gets it wrong on this synthetic data, which has the ground truth explanations. It's still correct to the model, right? It's that the model gets it wrong,
Okay.
not so much the explanation, that the explanation is objectively wrong. It's that we are being very faithful to the way the model has decided to model this task. So in that way, we still have a truthful explanation, and that's why the last column there, the relationship to model, is always 100% for the ground
Hmm.
truth, for the interpretable by design models, which also includes SEN and NAM. So they are always 100% truthful to the model, but we're trying to see the truth of capturing these underlying data patterns.
Right. Okay. Talk to me about the user-friendly explanations when it comes to interpretability. Obviously, this is important. And you have a table actually, I think, in the paper where, and you mentioned that one of the results was InterpretCC's explanations were preferred. Yeah,
By
talk to us a little
humans.
bit about that. How did you gather that information?
So, great question. InterpretCC explanations are user friendly because we tried to conduct an experiment where we tried to measure user preferences of different interpretable by design neural network models. And this usually hasn't been done before. If there has been a study, especially about fidelity or measuring different aspects, it's often focused on the more popular explainability methods like LIME and SHAP and counterfactuals and those kind of aspects, as opposed to these interpretable by design models, which are now just rising in popularity. So what we did was recruit 56 teachers via Prolific, which is a platform where you can recruit people for user studies. And these teachers came from a wide variety of backgrounds, but they are current teachers, often middle school and high school. And what we tried to measure was a couple of different things. So we gave them a NAM explanation, a SEN explanation, and then two kinds of InterpretCC explanations, the feature gating and the group routing. And for SEN and NAM, as well as InterpretCC, we had educational experts come in and craft the templates that were the way of proposing and sending this explanation. And we also conducted this experiment over a series of, I believe, 7 or 8 pilot participants. So we really tried to refine the study structure. There's still a lot more to do, of course. This is just an initial look. But what we found was that when teachers were evaluating explanations of student behavior across SEN, NAM, InterpretCC group routing, and InterpretCC feature gating, they oftentimes, and in pretty much every case, preferred an InterpretCC explanation. And we evaluated on 5 different axes that are pretty common for explainability user studies. One was about usefulness. How useful is this explanation to understand the prediction?
Mhm.
Trustworthiness, should I trust the model based on this explanation? Actionability, this explanation lets me know how to give feedback to the student. So essentially, this is a direct use case of this kind of work. Completeness, does it have sufficient detail? And conciseness, every detail of this explanation is necessary. So really trying to optimize these user-friendly aspects of how the explanation is conveyed and kind of the format in which the explanation is provided, as opposed to other evaluations, which are often on the stuff that we had just discussed, which is, are the explanations faithful? You know, are they consistent? So the angle that we took on it is really how useful are these explanations? And what we found, especially doing the user studies, was that in general, InterpretCC explanations were preferred because I think especially of their conciseness
Mhm.
and the way that they were described. Because, for example, with the SENN concepts, they often felt that these explanations were, I would say, more complete than the InterpretCC explanations. So that is the one axis that we failed on. Even though it's a bit surprising because they should all be the same level of complete because they're the exact same level of accurate. So it really depends on the user perception. In pretty much every other axis, InterpretCC did better. And we think this is because in the SEN explanations, it really has a lot of these different features because the way to describe a concept is describing which features were highlighted the most of those examples. Because as we were saying, it's really hard to understand um,
Yeah.
these concept-based explanations in this kind of field. Um, but turns out users actually liked it more for the completeness because they really felt that they got the really full picture of what was going on.
Okay.
Like the visualization was really detailed. But in terms of usefulness, I think both InterpretCC models did better than the other ones, as well as in actionability, which were kind of the two that we focused on the most, because we wanted the granularity of the explanation to be both customizable and useful to the downstream audience, and kind of understandable at a higher level.
Okay, and the human experts, let's call them, they were really evaluating the user friendliness of the explanations, not the correctness of the results.
So you're touching on a really useful topic and a really important one, which is how do you judge whether explanations are correct? And in these kind of fields, especially these kind of human-centric fields, let's say in education, where we're looking at student behavior, all of the features are meaningful. And what we've seen in kind of my previous work as well, with several teacher evaluations as well as student evaluations, people can convince themselves of pretty much any explanation. And this is also true in other fields, like for example, in healthcare, etc. If a lot of things are informative, if things look a similar way, or there's this notion of kind of trusting a machine's reasoning. So in this case, I guess the point is that the explanations are 100% correct to the model's underlying decision logic. So
Mhm.
to ask people to validate the explanation is just validating their perception of the explanation, because we know that by design, the explanations are correct to whatever the model decided, because the explanations are used to make the prediction. So because the explanation comes prior to actually even the prediction, we know for sure the explanation is correct because it was what was used. Um,
Right.
for our model, as well as for SENN and for NAM, and you can think of it also as like a decision tree, right? Like when we have a decision tree, it has a specific pathway, and that pathway already exists before a new point comes. So when the point
Okay.
comes, like the pathway that it follows is for sure the pathway that was used directly to make the decision. Asking these users to validate the correctness of an explanation is just whether those points align with their logic and underlying models, which we know that teachers from different backgrounds, and this was a paper called Trusting the Explainers from LAC 2023, which we had presented exactly this kind of user study where we asked teachers to validate explanations and tell us which ones they preferred more, because we thought that their model of what was correct was more accurate. And maybe certain explanations made more sense than other kinds of explanations. But it turns out they all have different perceptions of what causes student success. And therefore, they all prefer different explanations. And they don't even consistently prefer explanations from the same explainer. So, all of that to say, humans are unreliable correctors of explanations, I think, in these settings specifically. So our focus was a bit more on creating a model that would for sure provide explanations of what the model is doing. And then the
Right.
correctness of this would have to be evaluated in the situation and for the task. In
Yeah.
regards to the correctness of the models, that's exactly what our experiment 2 proves, because the
Okay.
matchingness of the underlying data patterns, because that is the correct explanation, basically shows that our model is able to capture those correct explanation patterns. So we know for sure that pretty much a lot of these, but definitely our model as well captures correct patterns of explanations. And then the second part is just about user perceptions.
This is something I'm really interested in. Obviously, interpretability and explainability can help us trust model outputs and can go a long way maybe in our, us i- having actionable insights on, whatever domain that we're using them in. But do we stand to gain a deeper understanding of patterns of correlations or causations between different parameters that we might have been overlooking by having the kind of level of interpretability that you're discussing or that InterpretCC could provide?
For sure, for sure. And I think you bring up a really important point, because the exact objective of why we care about explainability is to not have models that are incorrectly biased, right? That are making decision logic that actually we completely disagree with. So that transparency is kind of the first step to enabling these kind of fair models. And so if someone were to use this kind of model, they would see, like, on the scale of an individual, what exactly their explanation was. But let's say they used it a lot of times, or they used it over their whole class, and they could see in which areas this model is primarily making decisions, what kinds of logic it likes best, etc. And that might let you know that, hey, actually it's focusing on super the wrong things. I need to train a new
Mhm.
model, or I need to not use models for this. And those kind of conclusions are exactly what we want to build, which seems counterintuitive, right? Because on one hand,
Right.
we're like, yeah, let's build the models. But I think it's really, really crucial, especially now with such a big jump in LLMs and kind of the field as it is today. It's super important to be building this interpretability into models, not trying to ask for it afterwards. Because if you look at LLMs, what they will do is just give you an explanation that sounds nice, but might not actually be what's going on internally. And I really stress that this kind of guaranteed interpretability, this interpretability by design, the explanation being part of the decision making process, is what is crucial to actually build trust in these models.
So, what are the limitations? What are some of the limitations of the work as it is right now, anyway?
Several. So there's definitely a lot of room for improvement. Although we do think these models are ready to be used in a variety of different use cases, and we urge people to try them out. So the first I would say is with the user study. We looked across one domain area, and we would highly recommend that the similar kind of user studies need to be done across a lot of different domains
Yeah.
with the newest interpretable by design models that come out to really evaluate and see what is important to do in these areas. And I think it's a really crucial way. This area of how we can present explainability insights to users is actually really, really important and crucial because that's what actually people see, and that's what can have a very large impact on making sure these models are used. And then I would say that in terms of InterpretCC training, the model architecture is intuitive and actually quite useful, and it doesn't take a lot of code to make it work, etc. And we also provide all of our code open source. But what we would encourage is trying to find even better training procedures, because sometimes it's a little bit finicky. It's sensitive to certain parameters. For example, in the Gumbel sigmoid, what threshold you choose of like which parameter
Mhm.
you use can impact a lot the predictions. And we have those sensitivity experiments in our appendix. But we would also, I mean, it would be really interesting to see across a lot of different data sets what those kind of experiments can look like. Other than that, I think it's ready. We'd love to see it used. It would make us really, really happy to see it across different areas, or for people to try it and either like the idea or not like the idea. And overall, there's of course a lot more work to do also on evaluation, comparative evaluation of different interpretability techniques, etc. But we aim to provide kind of a first entry into this interpretable by design comparison space.
Yeah. Now, kind of extrapolating out of the paper a little bit, in your opinion, do you think that there should be interpretability standards attached to models, like mandates, I mean?
Ooh, that's a tough one. Let me think about it. Should there be interpretability standards? I think that, in an ideal world, yes. I feel like legislation that says, we really need an interpretable model before deploying it in these kinds of use cases and application domains might stifle the immediate productivity of the domain,
Hmm.
but would lead to a broader focus on these kind of models, and would urge people to really have that now. And I think this is exactly the crucial point where this becomes important, right? Because our language models today don't have that interpretability.
Right.
And we are using them way more and more and more. So uh, I think I would stand behind some kind of interpretability requirements, or at least like a gold standard, or that people trust the model more when it comes with these like certificates or something like this. I think it would be really important to implement, especially now before it gets used for everything and anything already.
What's the next step for Interpret CC? Or is there a next step for Interpret CC?
For InterpretCC, so actually we had a paper that came out after the initial preprint of this work called
Okay.
Interpret3C, which is all about using this for clustering, which actually
Okay.
got the best student paper. It was one of our interns over the summer
Oh,
who did this
congratulations.
extension. Yeah, she did a great job. Go Isadora. And it was all about how you can use this kind of model for essentially making all input points sparse enough that you can then have like interpretable clusters on default. Because if
Mhm.
you're adaptively selecting, let's say, the 3 features or the 6 features or whatever is relevant per student, and then you cluster based on this, um, accounting in a smart way for the difference in the number of features per student, etc., you basically get these clusters that are inherently interpretable without you having to do any analysis. And so, especially in our labs here, I'm part of the machine learning for education lab as well as the machine learning and optimization lab. But especially in the education lab, we're really focused on how we can bring these models without requiring too much human effort in ways that
Hmm.
are interpretable and secure and accurate, and helpful for students and teachers and also parents and the stakeholders in the space. So I think Isadora and our collaborator Paula did a really great job in trying to transform this into the kind of the clustering scenario. And I can imagine that from here, there are probably lots of other extensions into generative models, into
Yeah.
multimodal approaches. There's quite a lot of work still to do, of course.
This paper is being highlighted at, is it ICLR or
Yeah,
which?
ICLR, exactly.
ICLR. Okay, and then you have another related work at AAAI. What's you can share about that, but what other work do you have coming up? What's exciting? What new things do we have looking to look out for from you, even if it's unrelated to Interpret CC?
Sure. So hopefully graduating. So my private defense is
Okay, that's
actually
a big one.
very soon. So fingers crossed. And opposed to that, actually, me and one of my lab mates are co-founding a startup in the personalized learning space. So essentially AI for education and trying to really bring both interpretability and user friendliness in a new way to do kind of online and personalized learning. So watch this
Oh, really
space. We're
cool.
working on exciting things. The company will be called Scole. So if you want to keep an eye out for it, that would be great. And yes, the paper we have coming up at AAAI is coming up soon, and it's actually on that part that I mentioned, communicating explanations in an effective way to different kinds of stakeholders. And what's really cool about this paper is that we actually use social science theories of explanation written by, like the old ones from philosophy and from
Hmm.
psychology, and use them as prompting strategies in this zero shot chain of prompts LLM framework to take an explanation from, let's say, Lime or SHAP or any of these interpretable by design models and kind of express it in this hybrid way with both visuals and text in a way that's super actionable for students about their behavior. So instead of getting only their mid-semester feedback evaluation, whenever they want, they can
Yeah.
get like an on-demand feedback of how they can improve in the course or what they're doing or how these topics relate to each other, etc. Those are that work is being featured at AAAI, and there's some great folks at the lab continuing this effort into interactive explanations and user-friendly explanations.
Oh, that's awesome. I'm really excited to stay up to date on your startup and on those papers. I'll have to read. I haven't read the one that's going to be at AAAI yet. Thank you, Venitra, so much for your time. I appreciate it. It was great learning more about you and about your work.
Thanks so much, Allison. No, it was really a pleasure, and it really means a lot to have you supporting young researchers like this, and especially really reading in depth their work. It means a lot.